guys, let's begin talking about nuclear forces now. Okay, so we're wrapping up the atomic structure unit, considering both nuclear forces and then nuclear mass and energy changes. So to begin, I want you to consider positive protons will repel other positive protons. We've discussed this a little bit in the past, but one way that helps me to consider this is think of it like a magnet. If you've got a magnet, it's got a north and a south facing pole. You can consider that north pole like a positive, the south like a negative side. So this positive, when lined up with another positive, causes a repulsion. Okay, these will push away from each other. If I lined up a positive to a negative, there would be an attraction and they would want to get close to each other. And you see this when you flip the magnet over. So in the same way, electrical forces cause a proton and another proton to be repelled. Okay? A proton and another proton don't want to be near each other. A proton and an electron, on the other hand, would be attracted to each other. So the thing that I want you to think about is this, though. If we recall, the nucleus has protons and neutrons, and then outside of that, in the electron cloud, we have the electrons. Well, these protons, they repel each other. They don't want to be near each other. So we ask ourselves, there must be some kind of a force present that causes them to want to stick together. And these are, in fact, nuclear forces, okay? Forces of the nucleus that hold it together overcome the electrostatic repulsions of protons. So these repulsions basically are disregarded because the nuclear forces are so strong, it's forcing them together. This is why protons and neutrons are tightly packed together in the nucleus, which is what we're seeing here. Okay, a tightly packed center of protons and neutrons, and then electrons are flying about on the outside. Electrons have a ton of energy, which is why they're not smushed together in there too. However, they are attracted, so they're not going to fly off randomly off on their own. So another thing that we need to be aware of is Einstein came up with his energy equals mass times the speed of light squared relationship. Okay, so this equation lets us know that a change in mass is related to a change in energy for any kind of a process. Changing the nucleus through nuclear fission or fusion results in a very small mass change, but it's enough of a mass change that it gives off a lot of energy. Okay, so when we think of chemical reactions, right? Chemical reactions have very small, like incredibly small mass changes. So small that the energy change, it's a reasonable energy change. It isn't that much energy. What you need to be aware of, though, is the speed of light. 2.99 times 10 to the 8th meters per second. 2.99 times 10 to the 8th. This is a massive number. Okay, so even if my mass is small, it's multiplied by a very large number that's squared, so even a small mass can produce a lot of energy. Okay? Now, there are two different processes that we need to be aware of. First is fission. So this is my fission process. What happens is a neutron is going to slam into a uranium-235. This is one example of fission. Okay, it hits uranium-235, so this is going to cause this to become uranium-236. That uranium-236 is an unstable radioactive isotope. What it's going to do is, in turn, the nucleus will split. It splits into two lighter elements, and it also shoots off some additional neutrons, and here's the kicker. It is going to give off a lot of energy. Okay, a lot of energy is going to be released in this process because we have a small mass change. Okay, when this nucleus splits, we're going to have a mass change, and it's enough of a mass change to have a very perceptible energy. So the next thing that we've got to consider is fusion. Okay, so this is an example of fusion. Fusion is when you have two isotopes of hydrogen, okay? Hydrogen 2, which is called deuterium, and hydrogen 3, which is called tritium. So the deuterium and tritium come together, and when they join, they're going to fuse to form helium-5. Okay, so helium, we now have 2 protons, so that means this is a helium. With these 2 protons, they have 3 neutrons, okay? And one of those neutrons is not going to want to hang around because this is radioactive, it's unstable. So what will happen here is we have another release, okay? So just like in fission, when these neutrons are released, we're going to have a massive amount of energy when this small mass change occurs, okay? So be aware, these are the 2 kinds of radioactive change that are going to release a lot of energy. Now let's go and consider some practice problems. I will give you a second. You can pause. Yay, I assume you paused, and we'll move on. 2 protons will blank each other. They will repel. Okay, they don't like each other. So 2 protons would repel each other. So the question is, why are protons held together in the nucleus? Because nuclear forces are stronger, or they overcome the electric or the electrostatic, we call it the electrostatic repulsions. Now, the release of energy in nuclear reactions is explained by small changes in, you recall the relationship is energy is mass times the speed of light squared. So the release of energy, the change in energy is a result of a change in mass because the speed of light is a constant. So small changes in mass. A large unstable nucleus breaking apart is known as, so this is one of our 2 types of nuclear radiation. This is fission, okay? It will break apart, known as fission. Now, small hydrogen isotopes, our deuterium and our tritium, come together to form a helium nucleus, and this is known as fusion.